Hello everyone, my name is Renos Zabounidis, and today I'll be talking about my work dubbed Introspection and Theory of Mind Agents. As autonomous learning-based systems rapidly become a part of everyday life, it is important that they be able to complete their jobs in a socially aware context. Instilling these systems with human-like empathy and social skills, however, is a very non-trivial task. As humans, we can regularly, rapidly infer other humans' beliefs, desires, and intentions, using them to predict their future actions. However, in a computational framework, such inference would require knowledge of latent characteristics and states which are almost entirely inaccessible and computationally intractable. So a good first step to looking on how to solve this problem is to look at how cognitive psychology tells us the brain solves it. And so cognitive psychology tells us that the brain defeats the curse of dimensionality by building layers of abstraction. So humans and other animals have the cognitive capacity to attribute mental states to itself and others. This is what's called theory of mind, and in doing so, humans never really predict the exact mental state of others. We do not, for example, attempt to simulate the individual neurons of others' brains, nor do we attempt really to simulate any part of their brain at all, nor can we, since we never have direct access to the mind of another. Instead, we defeat the curse of dimensionality through attributing beliefs and desires to others. So, in doing so, theory of mind has become a backbone explanation for a broad set of cognitive abilities, which range from learning languages to judging the guilt or innocence of others. So, it's quite a successful theory. And so, the question now is, how do we apply theory of mind to artificial agents? And so, on the computer side, there have been several computational models that have been developed to describe human behavior. The largest of which are what's called Markov decision processes. MDPs can be used as models of decision making in both human and artificial agents. And so MDPs are defined as a tuple of states, actions, transition probabilities, a reward function, and a discount factor. And the typical, in order to model behavior, we essentially learn an optimal policy given this tuple. But in this case, we're interested in the inverse reinforcement learning task, which is when our MDP is modified not to have a reward function and instead has a set of expert demonstrations. Uh, and so in this formulation, we attempt to learn a reward function, and in doing so, IRL can be seen as learning a theory of mind. For example, instead of learning desires, we learn a reward function. Instead of intentions, we have a policy. Instead of beliefs, we have a reward model, et cetera, et cetera. So from now on, we can kind of use IRL as a stand-in for theory of mind under the assumption that learning one gains us the other. So some previous work on IRL. Firstly, we have Bayesian methods, which impose and search a prior distribution over reward functions. Next, we have maximum margin IRL, which chooses a reward function that most separates the optimal and second best policy. And then lastly, we have gradient-based approaches, which optimize a loss function with built-in penalties, such as the LC norm of deviations from the expert's demonstrations. Our work is an improvement on the approach of Hugh et al., who uses online gradient-based methods in order to estimate changing reward parameters. We use this approach specifically because it's the current state of the art in changing reward parameter based methods. A lot of previous work in IRL focuses on static parameters, and human beliefs tend to change quite rapidly. So being able to estimate changing reward parameters is quite important. So now we get to our research question, which is how can we recalibrate theory of mind models when they're out of sync with the true belief / intent state of what they're trying to model? And here we define introspection, which is defined from the principle that when a theory of mind model is out of sync with the true beliefs, the model must look at previous experiences. We do this essentially instead of trying to learn an additional model, which attempts to do better than the original one, because that's kind of a cyclic definition. Because if you have one that does better when the original model goes out of sync, then you might as well just use the current model. So anyways, in addition to our IRL assumption of being given a set of expert trajectories, under this under this framework, we additionally assume being given a set of reward parameters that were sampled from the original reward function. And so what we can do with these reward parameters is use them in order to learn the probability distribution over the original reward parameters in the reward function. And so we do this with what's called a normalizing flow. And so normalizing flow models arbitrary probability distributions by defining a series of bijective transformations from a base distribution. Look at the paper in order to learn more about them, but essentially they use a lot of different tricks and techniques in order to make this inference tractable over many dimensions. And yeah. So in our algorithm itself, introspection occurs when a change of intent is detected. And so a change of intent is defined as the KL divergence between two online IRL updates passing a certain threshold. And so when that occurs, introspection is activated. And so again, for introspection, we first train our normalizing flow, which learns the distribution over possible reward parameters. We then use a principle called nearest ship in order to motivate performing gradient descent on each reward parameter separately, keeping the others static. In doing so, we find the reward parameter that, if changed, most improves the likelihood of our model. And under this framework, essentially, we find one small parameter to change, and then we can essentially incrementally update our belief state that way. And so in terms of our experiment, we evaluate on a 20 by 20 grid world with 3 tasks. For the purposes of training the normalizing flow, we sample the reward parameters as follows. We have 3, and then we define certain meta parameters, which are sampled from a normal distribution, such that when we train our normalizing flow, it doesn't directly just learn the original function. And our normalizing flow consists of 5 coupling layers and then an additional Gaussian prior. And so to build our data set for training the flow, we sample 200 values of each metaparameter. And then for each metaparameter, the resulting 1000 by 3 time series is split into different slices, where each is 10 time steps long. And then these slices, these 10 by 3 slices, are shaped into a 30-dimensional vector, which is then inputted into our flow. And so in terms of our results here, you have the average reward parameter estimates over 50 trials. Our results turn out not to be significantly better or worse than Hugh et al. However, during the introspection update, we see that the reward estimate after the intent, after introspection, does significantly improve. And so we hypothesize this occurs because the pseudo estimate method in the online IRL kind of overwrites introspection after a couple of time steps. So in terms of future work, what we're going to look at doing is implementing introspection into the method itself. But for now, we know that introspection does indeed learn a better estimate. The question is just how to make that last. So I'd like to acknowledge the help of my mentors, Drs. Dana Hughes and Katya Sakara, who during the midst of a global pandemic and being online have helped me invaluably. I couldn't have asked for better mentors. And in addition, I'd like to thank everyone in the RISC program who has helped me edit my paper and really been amazing throughout the summer. And in addition, of course, to NSF and the other sponsors for making this all possible. Thank you.